Okay, so I think, in theory, you can get your Gadget 1 board right now. It's in the REL. I think a bunch of you already have. The stencils are here now, and we're going to get more paste. I guess we ran out of paste, so we'll order paste today. It'll probably be here tomorrow for office hours. So we'll have that done. So you guys can sort of do your boards. I think the office hours have been expanded or completed. I believe we posted that.
Yeah, the email should have gone out. Everyone should have gotten it. If office hours on Thursday and Friday.
But essentially, your Gadget 1, you can basically put together the same way as your mini Gadget. You got tweezers, you got parts, you stick them on the gooey paste, and then you can put them on the griddle. If you watched us do the griddling, it wasn't very complicated. It's not too much to screw up other than don't let your board sit on there so long that all the parts turn gold. That's bad. But maybe not completely bad. So today we're going to talk about Gadget 2, which is digital communications. But first, while cobbling together your library, I missed on a part. And if you're using a BCD to 7-segment display and the 7-segment displays, you're going to have to do a part substitution. Or your board is going to do this cool thing where every time you want to see a number, it's going to give you the opposite digits of the number you want to see.
So only like the segments that aren't in your number, which is
Probably not what you want. And that's our fault. We're sorry. We're going to order replacement LEDs. I'm going to order just all the red ones because I think we told you to do red. If there's some reason why that's not good enough, let us know. And they'll probably come tomorrow as well. So if you already soldered your LEDs, the best way to get them out is to use the hot air rework station in the REL. Get help if you don't know how to use it, but you basically just heat it up with the hot air, the part will just fall out. It's much better than trying to desolder each pin individually. And then super fun details, we're going to have to cut any of the VCC traces that go to the CA pins. And then we're going to have to sort of mentally substitute CC instead of CA on those pins and tie them to ground instead.
So it'll be a little bit of fun.
Little jumper, and anytime someone asks you, you can say, yeah, our instructor is screwed up. That's not my fault.
That should be fine. How many people are using the display?
Surprising number, there's probably 5 or 7.
You have 2?
Yeah.
All right, did you solder both in?
No.
Good.
So just for completeness, when we play with DCDs in the future, we're going to use this other chip, which totally doesn't look like the CD4511. It's the 4543, which actually has one of the I/O lines, which lets you select whether you're using common anode or common cathode chips. But the pinout is completely different, and it's much easier to cut one trace on your 7 segments than it's going to be to rewire like 10 traces on a little tiny IC. Which is sort of the downside of circuit bound technology. When you say rework, if you have like giant dip switches or wire wrap boards, you just change which your wire wrap it. But here you have to jump over the wires. So we're going to reorder those. Get them. Yep.
What do you mean by LED ROM or something?
So if you have 7-segment display,
7-segment LEDs. So the display module, which contains the numbered LEDs,
yeah.
there's a replacement module which will work with the driver. We just have to switch this one line. That's all. If you have RGB LEDs or other LEDs, this has nothing to do with that. You're totally fine.
Yeah.
This is just for the
those are much easier
number
to fix.
display.
If an LED part was wrong in a library, we would just tell you to solder the 2 legs to the other one. That's much easier to fix. These are a little ornery. So sorry about that. We'll get them ordered. We'll have the solder paste tomorrow, so you guys can continue with your Gadget 1. But just to start talking about Gadget 2, since this is a semester, we have to compress everything, keep you guys busy. And everyone loves it when the classes get more and more work towards the end of the semester, so we're going to do that. So just, first of all, what we want you to do is have a good idea for Gadget 1, or Gadget 2.
As opposed to Gadget 1's idea.
Yeah. Well, I think we like your Gadget 1.
No, Gadget 1 actually.
So we're going to give you a couple themes, because sometimes themes are good. And then there's also build your own. So if you've been dying to make some sort of like reciprocating seesaw circuit,
Now's your chance.
you can do whatever you like.
Give you plenty of rope to hang yourselves. It'll be fun.
Yes. But just to sort of give you some other ideas of like useful things to build gadgets for, there's a couple that we'd like to point out. One, there's Quality of Life Technologies. It has a weird acronym, but it's sort of a hot area of research. CMU and Pitt have a joint Quality of Life Technology Center. They do all kinds of really neat sensors and gizmos, basically designed to help people make their lives better. So some very specific things like a pedometer is a good example of a little tiny gadget that helps give you information. And if you've ever seen or played with a Fitbit, it's a little Bluetooth pedometer. You just keep it in your pocket. The only thing it displays is how many steps you've taken and like a happy face or a sad face if you've been lazy today. But then as soon as you go near a computer that has Bluetooth, it just slurps up the data, sends it to their server, and then you have like all this back-end server software that tells you very interesting things like, here's your day, you've been getting more active lately, here's less active. So it's a simple way to sort of get this data and then do something interesting with it. And so they're focused on how to get the data and do something interesting with it, but you could just get the data, like portable heart rate monitors, sleep EEGs. There's some neat stuff where they did actually just recording ambient sounds around and like also a sleep EEG, and basically they could tell that like when the dishwasher kicked on or something, or the furnace kicked on, it was way too loud and their sleep got worse. Or like when the central air turned on, their sleep got worse, and it was something about like the air quality went down, so their sleep got worse, their breathing got more erratic. So like fix your central air system. And like these are the sort of weird things that only become apparent when you go out there and actually collect all this data and do interesting stuff with it. So it's something to keep in mind, just how do you take sensors, how do you integrate sort of data logging into somebody's life in a way that helps them. And that's basically what your gadget wants, where we're trying to get you to take some sort of ambient information, like temperature or light levels, and then like tell somebody about it, so they can do something about it. Another sort of theme that we kind of like, is educational gadgets. So, fun things you can do to make things. Like the Makey Makey, I think, was a great example of just like not too complicated, but people could do all sorts of things with it. Like I want to get in a keyboard at home. That sounds like a great thing to just have in your kitchen. You either eat the banana or play a little tune. Why don't I have this? I don't know. Or like programmable robot kits, or toddler toys, but maybe just something that shakes and buzzes and does fun things, drives around.
Has some buttons, does some activities.
Vernier probes. Basically, there's all these kind of crazy probes that you can buy, like pH sensors, angle sensors, joint sensors, and you do all kinds of educational stuff with them, just by taking some very specific thing, getting information about it, and then letting people do stuff with this. And if you wanted to actually get this, if you know anyone who teaches or like works with kids or anything like that, you just say, hey, what do you do? What do you wish you could do? And usually people have problems.
Science teachers are often looking for ways to demonstrate certain physical concepts, which can be made a lot easier with.
If you can add explosions to a high school physics class, like people will love you forever. You just have to do it in a safe and controlled manner. Sometimes, a little bit of sensing and electronics can make that more interesting. And just general environmental sensors. And we need a lot of this stuff. There's a lot of pushes. This is an educational academic research facility, and there's actually a lot of money coming in just to get like water and air quality monitors, soil and pH. You want to tell them about the?
Sure. So there's at least 3 or 4 different groups at CMU right now that are doing nothing but some form of environmental sensing. So there's a sensor web project where they're deploying sensor networks, which are basically just microcontrollers like the ones you guys have been using, and they put them in fields at different locations to monitor stuff like the temperature and humidity over time to figure out why crops are growing or not growing. I work on a project where we take really simple sensors and put them in water and monitor sort of, we put them on boats that drive around, and we monitor things like water flow and pollution and stuff to tell whether fish are healthy or things like that. And then there's another project which is doing air and water quality monitoring with simple microcontrollers. The idea there is that you put a little sensor into your well water and then get back, conductivity and temperature, and know if the well water is sort of safe to drink or if it could be harboring bacteria because it's been warm enough for that sort of thing. So these are all very simple sensors that are using the same technology that you guys have access to with these projects, and they're actually an area of active research. There's active grants coming in where it's like, God, we really wish we knew what made crops grow and stuff like that. If only we could just put a bunch of little temperature sensors all over the ground, or a bunch of different light sensors, and see how much light this area of ground was getting over time. Then we would know how crops grow.
And, basically that's what gadgets are good, is this divide where there are people who want to do this science, but they're unable to because the engineering hasn't been done. You cannot simply buy these little boxes, or you can, but they're like fantastically
Hundreds of dollars or
expensive.
thousands of dollars.
And when you say, I wish to put 7,000 of these sensors per acre as opposed to like 2, because I assure you there are places where they have 1 or 2 of these big boxes and big solar panels on some farm, and they're here and there, and it gives them more information. But what we're getting to is where you can say, well, you know what, these mini gadgets probably only cost $6 to make. Could I just have 1,000 of them and put them somewhere and have them all talk to each other and record all this data? And that's basically what people are working on right now, and you can do the same thing. You have some interesting things that you want to sense and try to get this data back. All the technologies are really coming down. All of these sensors, 10 years ago, all these sensors were $50 or more. Now you guys can get them for $5 or less. Some are still expensive.
pH is still kind of expensive.
Wireless communications used to be ridiculous. Now you can buy Zigbee, which has sort of been rebranded as Bluetooth 4.0 low energy. You can use Bluetooth, you can use Wi-Fi.
So the stuff we're talking about today with serial communication will basically let you use a module which can go to any type of network that you can think of. Basically, people make modules which go from serial to Bluetooth to Wi-Fi to 3G. If you wanted to have a little gadget which can connect directly to a cellular network with a SIM card. Like once you have sort of these pieces in place, basically for $10 you can sort of do whatever you want.
And this is where, for a lot of your gadgets, we're nagging you about how much power does it use, how long does it run off your batteries, are you using batteries or power supplies? This is the kind of stuff where it starts to matter. It's like, well, I'm going to have this little tiny battery, I'm going to throw it in a field, maybe I'll put this tiny solar cell that kind of give it energy sometimes, maybe. We live in Pittsburgh, we know sun. We're cloudier than Seattle. So if anyone ever asks you which is sunnier, Seattle or Pittsburgh, Seattle wins. We just have less rain. And that starts to matter. Like, how do you put your thing in sleep mode so you're not using any power and can actually run off a single battery for 3 months or 6 months, so that when they say, well, we're going to do a research study in this field for 4 months over the growing season, it'd be nice if we didn't have to replace the batteries halfway through. Because they will, right? They'll grab some, scientists who'll have to run around in their little ATV driving through these fields and replace all these batteries because they're not engineers. They don't know how to make anything. All they're trying to do is collect the data so they can do their science. Okay, so that's environmental sensors. Or you can do whatever you want.
Yeah, some of you had good ideas that were a little too complicated for Gadget 1, and well, now's your chance with Gadget 2. You can, make annoying things to hide in your room for your roommates to find. Whatever you want. You'll have access to a lot more stuff with this. We're not limiting you to a specific set of parts like we were with Gadget 1 largely. And you'll have access to serial communications and digital communications in general, which means that if you are able to find something on the market which does some complicated bit of stuff, like Wi-Fi or 3G, you can drop that onto your module. And now you actually have a module which, for all rights and purposes is basically equivalent to something commercial in a lot of respects. So hopefully you guys have lots of secret great ideas that you've been holding out on us, and now we'll get to do all that stuff.
So just, build your use case. It still should solve some kind of problem, but, problem can be arbitrarily Gadget 2.
The problem with my roommate is too calm in his room solution, a buzzer which goes up at random intervals at 100
So
decibels.
let me just bring up the website well, not really quickly because it's our website, but so basically we have some details. In the end, you can build whatever you want.
So the one thing that we're constraining you to is that we are going to give you a set of 3 microcontrollers to choose from. So before, we told you you have to use the ATtiny. This time, we're going to introduce a couple of different options, which are all Atmel series microcontrollers. They all use the same tool chain, but some have a few more features than others. And we'll be going over that in the next week or
The
so.
only reason is we like it when you guys start from our skeleton file because it makes it easier for us to know that you hooked up the ISP correctly and that you're going to be able to reprogram your microcontroller. That kind of is a big deal when you're going to make a reprogrammable gadget. And that's what we're going to give you. For the Arduino, I mean, in general, we'll give you some links, but you can go find any Arduino. There are, I think, 37 different kinds by now. And you can use that as your reference. And I think we'll do the ATtiny, the ATmega, and the ATX Mega. That should be good enough for most people. You can talk to us, you can get something else, but in general, those 3 are going to keep you busy for quite a while. For the library parts, you're still welcome to use the Gadget 1 stuff. As you know, it's okay. So far we've only noticed one problem with the Gadget library, which was the wrong LED in the circuit. We'll find out what else we got wrong. So it's actually going to end up being on you for Gadget 2 to make sure that everything you use is right. And the worst thing that happens is it's wrong. You have to do something, substitute a part, and cut some traces. It's not the end of the world. And you'll either find parts online, which we're going to, we talked about on Monday, or you make them yourself. And either way, you want to verify them. Some I trust more than others. Unfortunately, Eagle is used by a lot of hobbyists, and anybody can sort of upload these random libraries. Some end up on Eagle's website, some end up on forums or the Arduino forums, and it's great because chances are somebody's already made the part you want. And if you're lucky,
They even made it correctly.
they made it correctly, but ultimately it's your problem. I certainly, one of the Altium, I think the Atmel, one of the Atmel libraries on Eagle's website, 2 of the pins were flipped. And I was just in there, and I verified it and checked, and I said, they got those pins backwards. Let me fix that. And of course, I didn't go back to Eagle's website and re-upload this corrected file. I just have my own fixed copy. So you have to watch that stuff. And you have to use at least one digital interface for your gadget so that we can say, yes, you used a digital interface. Here's your grade.
For most of you, if you're not interested in actually communicating with anything, adding just a debugging port that you can just print out stuff on will be sufficient.
And
So
that's
it's like
fine.
an easy serial interface that everyone can do.
And it's actually surprisingly handy. So as you guys do your code for your sensors, you'll be like, I'm getting this sensor value. I sure wish I knew what it was.
Now's your chance to know what
And
it
it's
is.
very nice when you can just, even if you only temporarily do it while developing, you hook up serial to your computer, and then your gadget is simply telling you, hey, I'm reading this thermistor, the value is 137, just FYI. And then you can speed up your development. And then we're still going to sort of make sure you make nice compact boards, and then the PCB specifications.
So that's the
from
details of
Gadget
the
1.
tracing and spacing. That'll just be from 30 for each, since that's a good standard size that everyone can manufacture. Okay, so for this theme assignments, it's basically a use case similar to what you were doing for Gadget 1, a little more in depth, since you're probably going to have to specify some stuff that's non-standard that you want to use or things like that. But that's the idea. Explain it to us, and then the timeline going forward is we will look over those use cases, discuss them with you, and then April 5th, we're going to go through the schematic and layout draft, and then a week from then, we'll order those boards, and then get them back another week later, build them up, and on May 8th, you will be doing a final demo of your exciting gadget, which does something amazing. and wows
Generally
and
both
wows.
gadgets. I
Both
think we do an
gadgets.
open house, people from who knows where we tell people, and then they show up and you tell them about your
Yep,
gadgets.
so you get to present off your gadgets, show off your cool little things, what they do. It'll be nice, you get to see what everyone came up with, get to show off the cool thing you
Not a lot of time, it's about a week for your use case, so
Yep.
think about it.
made. So we have to go a little bit fast just because we have to order this stuff and get it back and have you guys assemble it, so.
If you want to stick around until, mid-June, we could stretch out the deadlines, but.
This is more for the, we don't plan on you guys sticking around after the semester ends than us. We're here forever, so.
And the only important detail that's different from how Gadget 1 was handed in, April 5th, we're really looking for a schematic and the layout. So think about both things. This is especially critical because you guys are designing the parts. And especially for Gadget 1, a lot of people just kind of said, oh, I'm going to use this part, this part, this part. Let me just find these random library parts and just throw them in my schematic. And like, the schematic looks okay, we can talk about it, but your layout is just, has nothing to do with reality. It's very important that you be thinking about your layout, the part selection, while designing your schematic. So you need to be thinking about those things at the same time. And then there's about a week where we can do the back and forth and run you through the steps to get something that actually is producible. All right, so that's Gadget 2. Yep, requirements.
Yeah, this is
make
basically
things.
what's on the website. All right, on to the actual
So,
lecture for today, informational content,
Yes.
digital communication.
So digital communication is important. We're going to talk about serial first. It's the most basic. Everything, in general, technically all these are serial communication interfaces.
So basically, on Gadget 1, we kept you from digital communication, but digital communication is this general idea that we can signal things to each other using series of ones and zeros, in binary and so forth. And basically, for the purposes of microcontrollers, there are two major ways of doing digital communication. There's serial and then there's parallel information. And parallel is basically, I just put in n I/O lines and I make them either 1 or 0, and you just look at all of the I/O lines and get some value out of that. But that's taking up a ton of I/O lines, and unless you're going really fast or something, it's kind of a waste of your microcontroller because you're using all of your lines to just represent all of these bits at the same time. So what most modern communication interfaces use is serial communication. That is, I put in a series of ones and zeros over time. And there's a couple of standard ways of doing that microcontrollers support and that other peripheral devices support. So that's what we're going over today. And these should hopefully let you interface with a variety of different modules and sensors that use these same communication standards.
So the first is, I'm going to call this serial. This is like computer serial. You guys do not have serial ports on your computers anymore.
But you
Maybe
used to.
you remember dimly the good old beige boxes. They probably had at least one serial port on them. Nowadays, what we do is we either use a USB to serial cable. And in fact, the cable we gave you to charge your mini gadget, that's actually a USB to serial cable. So you have one already that you can use. We'll also talk about how you can mount a chip directly to your board that does USB to serial, and then you plug a USB cable into it. And so this, in general, you have very liberal connections. You can have a receive line, a transmit line, and then you need a ground reference. Otherwise, it has no idea whether that receive or transmit line is high or low. And what this is the RX is for receiving. So if the computer or some other device is sending data to you, it comes in on your receive port. And then you transmit on your transmit line, and that goes to the other guy's receive port. Technically, you could have unidirectional serial where you only transmit to somebody or you only receive from somebody. A good example of this is like a GPS receiver. If you actually wanted to use a GPS receiver, it's super easy. It talks serial and it just outputs data. It just tells you where you are. That's
So it
one
doesn't
purpose.
have an RX line because it has nothing to receive. So it'll just have TX and ground, and then it'll just spew information at you as long as you like.
Yeah, so if you wanted to get your universal frame coordinates at any time, you can just look up a GPS receiver, read it over serial, and it just tells you. And maybe it takes a couple minutes after power up, but you can just get this information. Now, the most common type of serial is this point-to-point asynchronous serial. So they're dedicated lines. They're completely independent. So you could be sending to someone, and they could be sending to you, but you're not doing it at any particular time. So like a good example of this is, let's say you have a serial port terminal open on your computer, and what you're looking at is just whatever the robot or your microcontroller is sending to you. So it could be saying, hey, here's my sensor value. It's 137. And then you programmed it to every second give you the new update. It says, hey, my sensor value is now 138. Hey, now it's 650. And you can just be getting this. And at the same time, you could be typing in key commands like S for change sensor ports, or C for blink the LED, or R for blink the LED in red. So these are happening at completely independent times, and you can do whatever you want with them. And the clock is asynchronous, so it doesn't trust that when you're receiving, the other guy has to be transmitting. For that, there's a different kind of serial. So the detail with serial, other than making sure that your receive line goes to his transmit and his transmit goes to your receive line, the other one as well. You have to, other than that, you also have to have the same baud rate because you have to agree on what your serial speed is. And these are all symbols or bits per second. It's not technically bytes per second, it's symbols per second. That's what a baud rate is, because there end up being a few extra details to it. And then usually they're all very common ones is 9600 to 115,200. If you've ever opened a serial port, your choices are generally some permutation between 9600 and 115,200. These are actually legacy. This is all based on a 3.46768 megahertz crystal, or some number like that, that everyone used back in the 80s. Whereas nowadays, people are running way faster, and you could easily just type in like 500 kilobaud or 1 megabaud. And generally the idea is just you have to get this decided ahead of time. So the biggest headache with serial when you're talking to a device you've never talked to before is, I wonder what baud rate it's at. So then you just start trying, like, is it 9600? I don't hear anything. How about 19200? No, still nothing. 38400? And you just keep cycling, and you're like, this is really annoying. I wish I knew what I programmed the baud rate to. And then once you've exhausted the list and tried all the weird ones, then you try flipping your RX and TX lines to see that you didn't get those reversed. And then lastly, the only other detail with serial, especially nowadays, it used to be that serial was basically always RS-232.
Which is a standard. This is recommended standard 232. So basically the idea is that these manufacturers back in the 80s came up with what they thought were good standards for signaling. And what they wanted was the ability to go over really long cables and, basically have a lot of noise and stuff like that, because that's what they were doing. And so they wanted really big voltage swings, because if you have a long cable, this really big voltage swing is easy to detect on the other side. So they said, okay, let's use negative 15 volts and 0 volts as our 1 and our 0. And then there's another standard, RS-422, which is a differential standard, so it basically just looks for a difference between two voltage lines. And then these days, you can often just use TTL, which is just your basic normal digital I/O of you're either connected to your power, which is 5 volts or 3.3 volts, or to your ground, which is 0 volts. Now, with these two, basically you need to do some level shifting. You need to get a chip which converts from your TTL signal of 1s and 0s being 5 volts or 3.3 volts and ground 0 volts to some crazy like 15 volts or 2. But you just buy that chip and stick it on your board, and then it just magically creates these RX and TX lines that are at the right voltage and do the right thing. So basically, you need to figure out which one of these you need based on what you're connecting to, but then you just plop down the appropriate circuit on your board.
And so these are called transceivers when they take a signal and convert it from one standard to another. And in general, if you were talking to an external device that came with actually has its own plastic housing, it's probably going to be talking RS-232 unless it specifically says 5 volt TTL or 3.3 volt TTL. If you were buying a chip from DigiKey, like an accelerometer or some other digital device, it almost always is going to have TTL. Usually, for board level stuff, everyone just uses TTL, and then only if you're going to go off board over wires of indeterminate length and quality, do you use a transceiver to some sort of noise immune system. Because I don't know if any of you have done a lot of breadboarding, but if you've ever done anything like serial, if you're talking at 9600 baud, you know, you can basically get away with like protoboard wires or even coat hanger type stuff. But as you go faster and faster, everything gets uglier and uglier, and like the bits stop making it from one side of the wire to the other, and your serial doesn't work. And then you have to like do it properly with good cabling, and then some of the stuff works.
So once you're at like Ethernet speeds of hundreds of bits per second, you actually have to consider that there are bits that are in transit along the wire at a given time. Like they are a pulse that is traveling on the wire. You can have certain numbers of bits on the wire, as in just flying through the cable at like a foot per nanosecond or something like that. And that you have to think about that because those bits, like as you're putting new bits on the wire, they're sort of traversing and causing.
Yeah, and these are sort of the details that we're running into now, because at some point, you know, light only goes so fast, and we're starting to clock
Electrons
chips.
go close to that fast, yeah.
You know, our chips are going at the gigahertz, and sort of saying, well, if I'm going to put these two things 3 feet away, you know, you have different you have multiple signals on the same piece of wire, and that's very strange to think about. Because you have to start worrying about the time delay.
Yeah, luckily for your purposes, which is one of the reasons why we stick to these simple interfaces, you can have a magic module which will deal with all of that stuff and convert to one of these low-speed buses, which you don't have to think about all of those things for generally. So if you're communicating at even 115, 200 BPS, you really don't have to worry about, you know, that time it takes for bits to travel through traces and stuff. So that's a lot simpler to deal with, which is why we focus on that. And these days you can get a module which converts to this low-speed stuff just fine.
So, don't want to go on and on about the same thing anymore, but just make sure when you're planning your use cases, what you're going to actually use, make sure you're aware that is it an RS-232 device, RS-422, RS-485, or is it a TTL voltage? So that, do you need an extra circuit, or can you just talk straight to it? So just to get into the nitty-gritty, so what actually happens, because you have no common clock, how do you detect when someone's sending you something? And the way it works is basically there's an encoding where the line is actually idling, and then suddenly a start bit appears. And what happens is that start bit is, you know, it's going to be at whatever frequency you're at. So let's say, let me just say we're going to talk at 1 kilobaud, just so I can do that in my head. And what that means is 1 kilobaud means that every symbol is going to take 1 millisecond, and it's going to be there for 1 millisecond. And the way it works is everybody who is going to have a baud rate, they actually are clocking at 8 or 16 times that speed. So they're actually checking this line at either 8 kilobaud or 16 kilobaud. And then what they're going to do is they're going to just kind of keep an eye out for a change to the start bit. And then once it sees the start bit, and you know, it could be off by a couple clocks. You know, it may not see it at exactly the same clock as when it started. And that's always the case because, you know, there's always electric details where the wire doesn't go from a 0 to a 1 instantly, or in this case a 1 to a 0. And then what it does is it detects it, and then what it does is it samples. It says, okay, I've detected a start bit. Now I'm going to kind of wait until what I think is the middle of that bit, when everything should be settled, and then I'm going to check again 8 or 16 clock cycles to see what the next bit is. So we see a start bit, then we see actually that's a 1, 1, 0, 1, 0, 0, 1.
Yep, inverted logic, you might notice.
Yeah, RS-232, they use inverted logic just to annoy people. The 80s were a strange time.
Yeah, so basically, the important thing here is that this protocol is well known and everybody has sort of the same idea of what it should be, including your microcontroller. So when you're configuring to talk to a device using this type of serial, you don't have to deal with how this is actually coming in or even what exactly is going on. what you have to do is match up the settings that your microcontroller is using with the settings that the peripheral device is using. And so basically, the settings for this are including the baud rate. You also have to set how many bits are in the data section of each of these little packets, how many stop bits are being used, because you can use more than one, a check of parity, which is another bit which can be adjusted to check the validity of the data, and if you want to use flow control. Now, back when modems were being used and stuff like that, flow control basically was a way of you signaling, like, I'm not ready for more data yet, you know, like, hold off, or I am ready for more data, you can send stuff to me. And these days, you don't really need it because your microcontroller can handle all the data, and it's deterministic, so it'll always be able to handle all the data. So the most common settings by far are having 8 data bits, 1 stop bit, no parity, and no flow control. But this is stuff that is available in the data sheet of whatever you're talking to. It'll tell you flat out, like, I'm transmitting with 8 data bits and 1 stop bit and no parity. And it may have flow control that's optional or something like that, but usually they don't care.
And flow control actually requires additional pins and additional wires to
Yeah.
it.
Flow
Which is
control
why
is-
most people don't do it.
It's literally 2 extra wires, and then if the wire is high, it means don't transmit, and if the other wire is high, it means the other guy's telling you that they're ready to receive.
And now this is actually where we go from symbols to bytes per second. So for instance, there's always 1 start bit, 8 data bits and 1 stop bit. That means for every 8 bits we send, we are sending 10 symbols. So when you want to calculate how many bytes per second we can do, it's not 9,600 baud divided by 8 bits.
Because you have these extra couple of bits to signal starts and stops.
So it's actually 9.6 kilobytes per second. No.
It's a little less.
Yeah.
But anyway, the point is you're going to get a little bit less than what you think you should get because of these extra symbols. But that's basically how this is configured. So these end up mapping to registers that you configure on the UARTs of your microcontroller. And it'll just be in the data sheet, like, do you want 8 bits or do you want 10 bits? And you'll say, no, I want 8, 1 stop bit, etc. They're just bit flags, you set them right, and then it just sort of works. You get in.
And we're going to talk about this next week. Next week, we're going to do specific code examples. Here's how you use serial on a microcontroller. We just kind of want to do the high-level stuff so you know what's out there. This is used everywhere. 99% of what you will do, these are the settings. Only really annoying things, these different settings.
So say we wanted to send
I think
hello.
we covered this.
Yeah,
I
and
really
this-
want to look at it more.
This is for you guys to look at this PowerPoint if you want to look back and see exactly how stuff would be encoded. But this is basically, if we were sending hello, here are the actual bit tables that would be sent on the wire as a sequence, and the sequence of what happens on the sender and receiver. But it's basically just us running through the same exact sequence for H, E, L, L, and O.